Welcome to the deep dive. Today we're using the material you sent over to really get into the world of shapes, polygons specifically.
Exactly. These are, fundamental building blocks in geometry, plane features. And our goal is to unpack what your source says, moving from the basics right into, well, quadrilaterals.
Okay, let's jump in. Your source starts with the definition of a polygon. It's a closed shape on a flat surface.
Right, made up of at least 3 straight line segments. And there are some key rules mentioned.
Yeah, it has to be fully enclosed by those lines, and the lines, the segments, they only touch at their ends, the vertices.
And crucially, they can't just form a straight line where they meet. No 180-degree angles at a vertex.
Right, because that would just make a longer line, not really a corner. The source has that 5-sided example, which shows it clearly.
Yeah, that helps visualize it.
And the names are pretty standard. The source lists them. 3 sides, triangle, 4 quadrilateral, 5 pentagon.
6 is hexagon, and it keeps going. Pretty straightforward.
Okay, but then it gets really interesting with the angles, the sum of the inside angles.
Ah, yes, the source has a great way of explaining this. It's about dividing the polygon into triangles.
Right, so a quadrilateral, 4 sides, you can split it into 2 triangles from 1 corner.
Exactly. And since each triangle is 180 degrees...
2 times 180 is 360 for the quadrilateral. Makes sense.
And a pentagon becomes 3 triangles, so that's 540 degrees. A hexagon, 4 triangles, 720. You see the pattern.
Yeah, it's always 2 fewer triangles than the number of sides, which leads straight to that formula that the source gives.
The Eden 280 degrees formula, where n is just the number of sides. Super useful.
And what's really neat is how the source uses it. It's not just calculating the sum, it's checking if a shape is even possible with given angle sum.
That's a key insight, yeah. The formula has to give you a whole number for n, the number of sides, and n has to be at least 3.
Like those examples, 2160 degrees, that works out to n14. Totally fine.
Right, a 14-sided polygon. Possible.
But 2400 degrees, that gives, what was it, 46 divided by 3?
Yeah, 463 sides. Which, doesn't make any sense. So, no polygon has that exact angle sum. It's a neat reality check built into the geometry.
It really shows how the rules connect. Okay, so let's zoom in on what the source highlights next. Quadrilaterals.
The 4-siders. 4 sides, 4 interior angles, 4 vertices. And your source also mentions the diagonals.
Oh yeah, the lines connecting opposite corners.
And how the sides, angles, and diagonals relate defines the different types.
Okay, so what's the first type the source breaks down?
It starts with the trapezium. The main thing is it has at least 1 pair of parallel sides.
At least 1 pair.
Okay.
And there's a special kind.
Yes, the isosceles trapezium. That's where the non-parallel sides are equal length. And your source points out the consequences.
Right. Equal non-parallel sides means the base angles are equal, and the diagonals too.
And the diagonals are equal too. That one property forces the others. It's quite elegant.
Interesting how that works. Okay, after trapeziums.
Parallelograms. Now we need both pairs of opposite sides to be parallel.
Both pairs.
Okay.
And that parallelism leads to other things.
Definitely. The source lists them. Opposite sides have to be equal length, opposite angles have to be equal, and the diagonals cut each other exactly in half. They bisect each other.
So those properties aren't optional, they're baked in because of the parallel sides.
Exactly. And then the source talks about these special parallelograms.
Right, the ones that add more rules, like the rhombus.
A rhombus is a parallelogram, so it has all those properties, but also all 4 sides are equal length.
Okay, equal sides. Does that change the diagonals?
It does. The source notes its diagonals cross at a perfect 90-degree angle. They're perpendicular. And they also cut the corner angles in half, bisect the vertex angles.
Lots of symmetry there. What about the rectangle?
Also a parallelogram, but its special feature is that all 4 angles are 90 degrees. Right angles everywhere.
Yeah, and its diagonals.
For a rectangle, the diagonals aren't necessarily perpendicular, but they are equal in length. That's its unique diagonal thing.
Got it. Which leads us to the square. The source had a nice way of putting this.
Yeah, it defines the square as a parallelogram. That's basically both. It has all equal sides, like a rhombus, AND, all 90-degree angles, like a rectangle.
Ah, so it inherits everything.
Exactly. Your source points out it is a rhombus and it is a rectangle all at once. It gets all the properties combined, equal sides, right angles, equal diagonals, diagonals bisecting each other, diagonals being perpendicular, diagonals bisecting the vertex angles. The works.
Wow, okay, so that structure, that hierarchy is really clear. So, recapping. We went from what makes any polygon a polygon, this idea of closed segments and vertex rules.
And that angle sum formula, the N2 check.
Right through to quadrilaterals, seeing how adding rules like parallel sides or equal sides or right angles creates this family tree. Trapezium, parallelogram, rhombus, rectangle, square.
And understanding these basic shapes and their rules isn't just, textbook stuff. It helps you see the geometry that's literally all around us.
It really does. So here's something to think about, a final thought maybe. How do these incredibly simple rules, just how many sides, how angles have to add up, parallel lines, how do they generate all the complex, strong, and sometimes beautiful structures we see? From buildings to bridges, even in nature. It's amazing what comes from these basic shapes.